Okay,
All right, welcome
let's
back. Let's go ahead
continue
and
here. Section 4.9. This section deals with redox, and let's go here and identify all of the sections here. So when we talk about redox, this name here can actually be broken down into two parts, the RED part and the OX part. The RED part is referring to reduction, and the OX part is going to be the oxidation part of things. It's important to know that in dealing with the reduction and oxidation, the reduction is associated here with gaining of electrons, and the oxidation is involved in the loss of electrons. And so it's important that we break this down. And when we do the redox, we got to keep track of all of the electrons that go through. You will be asked to balance, and you will be asked to balance in two categories, one in acid solution and another one in basic solution. And so each of these sections here of a reaction is going to have two parts. One part is the reduction, the other side is the oxidation. So when we look at this here, this entire piece right here, this is known as the half reaction that is associated for the redox. So this is the reduction half reaction. And then on the other side, this is going to be the oxidation half reaction. And so when we look at this in terms of a general equation, which we're going to look at here, a couple of examples, you want to make sure that when we get these half reactions, the half reactions have to be balanced both not only on the atom side of things, they also have to be added up and balanced based on the number of electrons. And if you have oxygen present in any side, you have to balance that out with very specific rules. So let's go ahead and do an example here. Let's move some of this over here to the right. And let's do this here. Let's use this color here. We're going to use yellow. And here is an example. So I'm just going to go ahead and do this here. So an example. Let me go ahead and write it up for us, and then we'll go from there. All right, so here's the problem. We've got on this side here, we've got lead oxide combining with iodine gas, going to form lead 2+, and then iodine with 3 oxygens, as we have here, iodate. This is an ion. And so the first thing that we want to go ahead and do is we want to make sure we identify all of the charges. So go ahead and do that. Let me go ahead and write that down for us over here on the right-hand side. So I'll do the steps here. 1, ID all charges. And so this statement here refers to identifying the charges of all of the atoms in the formula. So we'll go through here step by step. And that means here for the lead, notice here we've got oxygen. Oxygen is more electronegative than the lead. Lead is a metal, so it's going to lose electrons. But oxygen here, we've got 2 of them. So each oxygen is going to be able to accept the 2 electrons that it has a space to accommodate. When it does, it'll have a -2 charge per oxygen. So that's a -2 for each individual oxygen. But since we've got 2, the total charge on this side for the oxygens here is going to be -2 times 2, which is a total of a -4 charge. So this lead is going to have to be a +4 to balance out the charge. Okay. We'll move on to the next one here. Iodine is a diatomic in this particular case. There is no charge associated with that, so we'll put that as 0. Go to the other side. On product side, we've got the lead. Notice the lead now is a +2, so that's a difference from before. We'll pick that up here in a second. And then the next thing here, we go to the iodate. For the same reason that the oxygen over here had a -2 on the reactant side, the oxygen here will also have a -2. Iodine could be negative, however, oxygen is more electronegative, so the oxygen will have the -2 charge. So let's go ahead and label that. Okay, let's go back here. We'll put here a -2 charge. Since we do have 3 oxygens, so -2 times 3 means that this whole charge for the oxygens is a -6. So the total charge of this iodate is going to be a -1. So some charge plus a -6 is going to give me a -1. So clearly the answer here has to be +5. And so how do we do that? So let me just show you the really quick here. The math, the way you check this out, this is going to be a -1 charge. It has to be equal to the charge of the oxygens, which we've already said is a -6. And so when we add that to the charge of the iodine here, do the math. So -6 -6 on both sides, or we're going to add to both sides here. That's actually going to cancel the 6 here, and on the other side you're going to have a +5, and this is going to be associated with the iodine. And so that there is why we wrote up here a +5. Okay, so that's the math there. Let me go ahead and erase it. We don't need all this work, so let's go ahead and erase that, get it out of the way, and let's continue on. So that's the first step. Now you've got the charge of everything, so the next thing you're going to do is you're going to check to see what charges changes on each individual atom. So you want to go atom by atom, and we're going to go over here from the left-hand side. We're going to see here, notice we've got a +4 for the lead, so we go to the other side, look for lead. Notice here the lead is a +2. So now that we've identified it, I'm just going to go ahead and put a row like this just to help us out. We know that this is going to change. Excuse me. We know the charge is going from a +4, it's going to a +2. Now you don't have to write it like this, but I'm going to write it like this just because it's easier to do that. So notice here the charge was a +4, and the charge went down to a +2. So what could have happened to cause that charge to come down to a +2? Well, the only way that we can actually get that charge to actually go from a +4 to a +2 is if you gain some kind of negative value here. Some negative value, when added to +4, will give you a +2, which means that here you must have had at least 2. And so here you must have gained a negative charge, but here -2 is associated with 2 electrons. And so that's how we gain that. So if you want to see that down below here, so a +4 minus 2 will definitely equal +2. So that is correct there. Let's continue our search. Go down the next line here. Notice the oxygen has a -2 charge. On the other side, oxygen has a -2 charge. So the oxygen's not involved here. Exactly. So it's not the one that's actually changing electron count. But we go to the next atom. Iodine here has a charge of 0 on the reactant side. And on the product side, the iodine is going to have a +5. So that's definitely going to be one that's actually changing charge. And so let's go ahead and put that there as well. So let's label it like this. And in this particular case, the iodine is going from a 0 charge going to a +5 charge. Now, if you think about this for a second, the charge here at the 0 means that you have the same number of electrons, you have the same number of protons. So if you're looking at it from a pen count perspective, the pen count here for iodine is neutral. You have the same number. But in order for you to move from 0 to +5, then you must have lost electrons here, because that's the only way you're going to get a plus charge overall. So when we write this out, in order for you to go from 0 to 5, you must have lost 5 electrons. And that's going to be important for us when we actually balance it out. Okay? So now that we've got this, the next step here is going to be the identify the reduction side of things and oxidation, which we just did. But before we move on, let's go ahead and clearly identify it. So when you lose electrons, that's oxidation. So the bottom part here is oxidation, and the top part is going to be the reduction, because that was the side that was involved with gaining electrons. So the next step for us is going to be to go ahead and split out the reactions. So here we're going to separate the half reactions. And so that means that we're going to put the reduction first, the oxidation next. And so let's go ahead and do that here. On the left-hand side, let's get the reduction side. And so we're going to get PbO2, and then that's going to go and produce Pb2+. And we'll just separate that out here. And then the oxidation side of things, that's going to be I2, and this is going to go form IO3-. I'll just go ahead and put the charges here just to make sure everything's up and up, just so we can actually see everything as we follow along. Okay, so that's what we've got there. All right, so the next thing we want to do is, just before we get going, we want to make sure that we have the right number of atoms on either side, at least before we do anything with the oxygens that might be present. So here, notice we've got one lead on the other side. So at least on this side, on the reduction side, the leads are balanced out. We will need to deal with the oxygens, but we'll deal with that here in a little bit. Let's go to look at the oxidation side of things. And on the oxidation side of things here, let's move it this way. oxidation side of things here, we've got 2 iodines, but we only got 1 iodine over here on the right. So we're going to have to deal with that now. So let's go ahead and put that and put a value here for the iodine. We're going to have to kind of label that. Let me use a green color here. So we'll have to put a 2 coefficient in the front. Now the next step for us is to go ahead and balance out with the oxygens. We have to deal with those oxygens. So here, I'm just going to put here balance. And I'm going to put here the oxygens. And so remember what we said here, when we're balancing with the oxygens, what this really means is what we're going to add here means that you're going to add H2O for every oxygen that's in the formula. So let's go ahead and do that here on the left-hand side. On the left-hand side here, notice we've got 2 oxygens. So we need to add 2 waters to the opposite side of the reaction to make sure we balance that out. So let's go ahead and do that now. And so here, 2 oxygens, we're going to rewrite this equation here. And we're just going to say PbO2 goes to form Pb plus 2. And then here's where we're going to add the waters. And let me go ahead and add those in blue. So plus H2O, and we need 2 copies of that. Now we're still going to need to deal with this, largely because now that we've got the 2 waters here, the next step in the sequence is that we're going to have to deal with those oxygens. So here on the problem, we've got a total of, every water molecule has 2 hydrogens, and there's 2 copies, so there's a total of 4 hydrogens on the right side. So what we need to do here is add 4 hydrogen ions to the left-hand side to balance out. So let's go ahead and move some stuff here. Let's move this particular piece right over here to make some space, and then we can zoom in on here and write that information here. And I'm going to go ahead and write that down here in red. So we're going to have 4 H plus ions. And so when you look at the numbers here, let's go ahead and zoom in a little bit. When you look at the numbers here, you're going to see that we've got 4 hydrogens on the left side. We've got 4 hydrogens on the right. We've got 1 lead on the left, 1 lead on the right. Now here we've got 2 oxygens on the left, but now because of the coefficient 2 and the 1 here, we've got 2 oxygens on the right. So it appears to be balanced, at least in terms of atoms in the solution. The problem is we haven't taken into account the electrons. And so since we know that this particular side of the reaction here is the reduction side of things, now we're going to have to come back up here and take into account the electrons that were associated with the reduction, which were 2 electrons. And since they were gained electrons always show up on the reactant side. So we're going to have to accommodate 2 electrons over here on this side. So the way we'll do that is I'm going to go ahead and move this here, make a little bit of space here, make it just a little bit smaller and move it over to the right. And I'm going to move this as well just to make sure we can accommodate everything here. And I'm going to do the following, move it over. It's a little bit of a challenge here. We'll do it like that. And then we'll put the electrons, and we'll put those electrons in green. And so when I do this here, we should have here plus 2 electrons. And I know that's not pretty there the way I've written it down, but you can see that I've got the 2 electrons on the one side. Okay. We'll go ahead and do the steps again over here on the right-hand side. And the only thing I need to add here just to make sure we're keeping track of everything is we need also here for step 5, we want to balance the hydrogens. And so remember here, this particular one said that whenever you're going to have for every hydrogen on one side, so for H's here, you want to add 1 H plus on the opposite side. So that's what's going on here. So let's go through the steps again here, steps 4, 5, and then we'll add the last step here for the electrons. We'll add that. All right, so we're going to do the same thing to the right-hand side, and let's go through this one step at a time. Here, the iodine, as you can see, we've already got 2. We've got 2 on this side, so we've already handled that. But notice here we've got 3 oxygens on the right-hand side. So what that means that we need to do here is we're going to take the 3 times the 2 because we added a coefficient, so we have a total of 6 oxygens on the right. We need to make sure that we add 6 waters on the left. So let's go ahead and do that. And so let me zoom in a bit. And we'll go ahead and take care of that. So let's say here we've got 6 H2Os, and then we're going to add to that plus I2, and this is going to form 2 copies of IO3 minus. Now the next step for us in the process, remember we have to go ahead and take care of any hydrogens that we add. We just added a total of 6 molecules of water, but the hydrogens is 2 times 6, so that means a total of 12 hydrogens, which we have to add to the right side. So let's go ahead and add those. And so here I'm just going to go ahead and add them right in line. So this is going to be plus 12H plus. And that's going to be what we need to add there. All right, so the last thing that we need to do now is to take into account all the electrons that were involved in the oxidation side of things. So we've got that number right here. There were 5 electrons that were lost. And so that means that these 5 electrons have to be accounted on the reactant side. Now I'm running a little tight on space here, so what I'm going to do is I'm going to rewrite the equation down here below with all of that information. Okay, so I've got that written down right here. And so what we need to turn our attention to now is we need to make sure that both sides of the reaction are balanced in terms of electrons. And so notice here on the left-hand side, we've got 2 electrons, and on the right-hand side, we've got 5 electrons. And so that's going to be a problem for us. And so we need both of these numbers to be the same. We need a common multiple between them. So the only thing that's common between the 2 and the 5 is that we actually do this as a times of the other number. So if I take the 2 over here on the right-hand side, left-hand side, I mean, and multiply that by 5, that'll give me 10 electrons. And if I do the other one and multiply this by 2, that'll give me 10. So what we need to do here is a little bit of a cross multiplication on both sides. And so I'm going to go ahead and do that here in purple. And I'm going to multiply the left side. I'm going to multiply here. I'm going to do this times 5 to accommodate that. So I'll write here times 5 right above. And I'll do the same thing here. And I'm going to do here times 2. And I'm going to have to redistribute that number all the way through for each of these numbers down here at the bottom. Okay, and so let's go ahead and do that. The next line, you're going to see all of that worked out. Okay, so the only thing that I see here that I kind of need to adjust here is the 12 here. That needs to be a 2 on the iodine side of things. And so let's go ahead and do that here. I need a 2 right here for the iodines. And everything should be fine now. Everything looks balanced. So the next step for us is to go ahead and add these 2 reactions together. Let's go ahead and add them, and I'll show you that work here in a second. So we've got everything here. What I'm going to do at this point is I'm just going to go ahead and put a line here because we're adding these. And let's go ahead and zoom in on this section here and try to see if we can cancel any like terms. It's going to be quite a bit of work, so let's go ahead and do that now. Okay, so here's that section zoomed in. And notice here we've got a couple of items here. We've got 10 electrons on the left, we've got 10 electrons on the right, and what we're going to do here is we're going to be a very similar process that we did when we dealt with net ionic equations. Remember in that section we dealt with spectator ions and we eliminated them from either side. Well, we're going to do a similar process here. Obviously these are not spectator ions, but these are species that exist on both sides, and we want to make sure that we get rid of any like terms in excess. And so here with the 10 electrons on the left, 10 electrons on the right, what we're going to do is just start going down the list and start canceling. So we don't need these 10 electrons here. And so we'll do that there. The next item that we'll do is we'll look at the hydrogens. Notice here we've got 10 hydrogens on the left and we've got 24 hydrogens on the right. So what we're going to do at this point is we are going to eliminate the excess that we have on the left versus the right. And the way I'll do that here is I'm going to go ahead and say minus 20 hydrogens. That will allow me to cancel this, but then I'll come over here to the other side and say minus 20 hydrogens here, and that will give me a difference. I'm going to go ahead and cancel it out, but I'm going to put the difference right above, which is going to be 4 hydrogens are going to remain. We'll do the next section here, and that would be the waters. Nothing else is going to be existing on both sides. So the PbO2 here exists. Let me fix this. I see the 2 parts missing. And PbO2 doesn't exist as an ion on either side, or does not exist in this form on either side. So we can leave that alone. The iron, the lead ion on the right-hand side is there. It doesn't exist as an ion on the left, so we can leave that alone here. But notice here now the waters exist on both sides. We've got 12 on the left-hand side, 10 on the right-hand side. The difference between these is going to be 2. So what we'll do is we will subtract 10 waters from the right. That will allow me to cancel this entire thing. So I don't have any more on the right, and we'll subtract minus 10 waters on this side. and that will allow me then to cancel this. But the difference is that we're going to have 2 waters left over. So I'm going to go ahead and write that up top, H2O. There. We've got 2 iodines left, and so that's fine there. And so what do we do now? What we're going to do is going to go through the entire list and write down whatever did not get canceled out, and that'll be the final equation we'll write down here at the bottom. So let me write that down and show it to you. So this here is the final equation. Notice here if we go through, count all the atoms, we've got 5 leads on the left, 5 leads on the right. 5 times 2 is 10 oxygens, plus these 2, that's 12 oxygens, and we've got 4 times 3 is 12 oxygens on the right. And here we've got 2 times 2, 4 iodines, and on this side we've got 4 times 1, 4 iodines. So everything's balanced out, everything's good. We've taken care of not only the oxygens, we've taken care of the hydrogens, we've also taken care of the electrons that are in place. And so at this particular point, this particular balancing here is going to be balanced for acidic conditions. And one way that you can know that you've got the acidic, notice you've got the hydrogen ions over here. So this is going to lower the pH there. And so let's go ahead and label it as so. I'll zoom out a little bit on this and show you here that this particular balancing here, let's go ahead and put a red box all the way around it here. This here is balanced for acidic conditions. Now, so we don't make this video way too long, what we'll do here is I'm going to take this same problem and I'm going to go ahead and balance it in basic, but I'll put that as a separate video here so that you can look at that. So that'll be like 4.9b, and we'll see you in that video.